What's cracking, guys? This is the second video in the Machine Learning with JAX series of tutorials, and in this one we're going to learn how to build fully fledged neural networks. So in the last video we went from 0 to hero, and in this one we're going to go from hero to HeroPro Plus. Yeah. Anyways, before we even start, let me show you this thing. So I open sourced a repo that's gonna called Get Started with JAX that basically contains, aside from these tutorials I'll be making, other useful like content that I personally used and found useful. So things like various YouTube videos, blogs, etc. So the second thing I wanna tell you is that you can basically open up these notebooks I'm using in these videos in Google Colab, and you can easily play with them. So you can just open it up, and the Python environment is already set up. So JAX and everything else is pre-installed, so you can just kind of run this and everything will work. Just run anyway, and this is going to work out of the box. So basically this, like the notebook for this second video is already checked in as the time I'm recording this. So you'll be able to open it up and maybe tweak the code as you are watching the video. So I think the best approach to get the most out of these videos is to tweak the code yourself, play a bit, and see whether you can learn something interesting. Awesome. With that out of the way, let's continue with the video. So let's first import the packages. We saw this in the last one. So we're just importing JAX, the NumPy API of JAX, transform functions that we saw in the last video. So grad, JIT, VMAP. In this one, we're going to learn about PMAP, which helps us parallelize the computation across multiple devices, which is very useful, as you can imagine, and yeah, other necessary libraries here. So the goal, as I said, will be to learn how to build more complex machine learning models, parallelize the computation across multiple devices, and yeah, basically after this video, you should be able to get started and build your own models. In order to get to the point where we can build neural networks, there's a couple of things we have to first solve. The first one is the problem of state. So when I say that, I mean the following. So JAX is basically uses the functional programming paradigm, which means we need pure functions, which means JAX does not love state in the sense that you cannot use your usual object-oriented programming type of stateful classes or functions. So we're gonna see a way around it right now. First, a short reminder from the first video. We saw that impure functions are problematic. So we saw this global variable g, and we can treat it as a state for the purpose of this section. Basically, what this impure uses global function does, it accesses g, which is external state, which is forbidden because this makes the function impure. And what happens now is when the JIT, when we call JIT on this function, it's going to cache the current value of g because that's a side effect. So it's gonna just cache the value 0. So that means the first time we call it, it's gonna run correctly. But the second time we call it, we're going to call the cached version of the function, which means 5 will be added to 0 and not 10. So in the meanwhile, we've updated g to 10, so the state is updated to 10, but that will not be reflected because of because we have impure function. So this is the trick you have to be aware of. And as you can see here, we get the correct result for the first call, but we get the incorrect result for the second call. So that's 5, and we should have gotten, I guess, 5 plus 10, that's 15, right? Okay, that's the first step. Secondly, we saw this pattern already. So basically, we saw that the pseudo-random number generator in JAX is not stateful, in contrast to NumPy's. And we saw this pattern where we create the state, the initial state, by just passing in the seed. And then, in order to get the next state, we just call this split function, and we externally pass the state. So that's a big difference compared to NumPy pseudo-random number generator. So I basically want you to remember this pattern. So we are inputting the state inside of the function. So split is not saving state internally. It's just taking it as an input. It's manipulating it somehow in a pure fashion and returning back some novel states. Whereas just recall that we were using key and sub-key terminology previously. I'm just want to stress out that we are basically I want to stress out this pattern, so that's why I'm using this new terminology. But yeah, you get the point, hopefully. Okay, so now let's see a way around this. And if I haven't made this already clear enough, let me just kind of motivate why we're doing this. Basically, if you're trying to create a neural network, for example, like there is a lot of stateful code when you're trying to build neural networks, especially in other frameworks such as PyTorch or TensorFlow. Basically, your model parameters are stateful, your optimizer is stateful. Atom is, for example, storing internally a certain statistics, so that means it's stateful. And also we have layers such as batch norm, which are stateful. Yeah, in summary, any useful program will have to have some kind of state, and we just need to find alternative way how we can handle it. So in this first example, we have a stateful class. It's called counter. We have this state called like n, which is basically the internal count. And we have the function count, which just increments this state by 1 and returns the current value of that state. Finally, once we call reset, we just set the state to 0, and that, I guess, all makes sense. Here we just instantiate an object of this class, and then we call 3 times. We call this count function, and as expected, hopefully we'll get 1, 2, 3, and here they are. Okay. So that all works like a charm, and this is something you're used to. Now, the problem arises here when you try to JIT the function. So let's reset the counter, and so that means the state is now internally set to 0. And now let's try and JIT the counter count function. So let's try and JIT this function here. Now let's see what happens with it. Once we JIT it, and we try to, again, run the same type of like a for loop here, the results are kind of surprising maybe, or maybe not if you're familiar with JIT. Basically, we get all ones. And the reason is, as I said, this count function is not pure because we are basically writing to an external state, as you can see here. So self.n is a state. Basically, it's not passed in as an argument. We are just modifying it externally. So that's bad. And what will happen is, so once we call reset here, n will be set to 0. And the first time, so once we JIT, the first time we call a JIT function, we're going to do the tracing, if you recall from the last video. And that means that basically on the first call, the function will return 1. And because we have a side effect, it's just going to learn how to cache number 1. And that's it. Now, let me just kind of try and clarify that. If we were to use make JAX-per to make this more clear, let me run this and see what the like underlying JAX expression is, and we can see it learned to just return like 1. So basically, the cache function has like the whole body of the function is something like this: return 1. That's it, and that's why we're getting ones, even though we are expecting to get increments. Okay, just to make this a bit more clear, if we were to call counter count function here, we'd expect the internal state to be modified to like 1. And then once we call JIT, it's going to be returning 2s now, hopefully. So if we correctly understand this, if I run this, we get 2s. And the reason is, again, it's basically tracing this function. The first time it's tracing it, the value was already set to 1. We add additionally 1, so we have 2, and we return 2. And basically, because we don't have any inputs, it's just going to learn how to cache and return those number 2. And again, if I were to do the same thing here, so count and call the make JAX-per, we're hopefully going to get like just 2 instead of 1 here. Let's see. And that's correct. Okay, we got 2 here. In any case, we have to find a way to avoid like creating these impure functions. So let's see what the solution is. We're going to define this counter state, like instead of defining a complex class, we're just going to have like a simple primitive data type here, so integer. So this version 2 of the counter is going to work the following way. So we're going to pass in the counter state, and we're going to return back the output as well as the state. Now this may be a bit confusing, n+1, why are we returning a tuple of n+1 2 times? I mean, doesn't make any sense, right? So the thing is, in general, this thing here will be state, and this thing here will be some function of the state. So here in the example of this simple counter, the output as well as the state are the same thing. So yeah, we're just returning n+1. But yeah, it doesn't matter. The whole point is we are passing in the state and we are processing it and then returning it back. In the case of reset function, we're just returning back the state 0, and that's it. So here we instantiate the counter. Here we call the reset, and as you can see here, compared to the version 1 of the counter, we are not internally modifying the state. We are just returning back the state here externally. And here we can see the pattern. So we call the counter count, we pass in the state, and we get the state and the value. We print the value, and we keep doing this. And so, yeah, I guess this should already be familiar. Basically, JAX, random number generators use this very same pattern. So this should work like as expected now. And as we can see, we get 1, 2, 3. But now let's see whether after we JIT the function, this thing will work or not. Let's call reset again. We get the initial state. Let's JIT the function and let's try and run this. And as expected, we're getting correct results even with this JITted version of the function, because we are externally manipulating the state and not creating impure functions. And yep, this is working as expected. And in summary, let's see the pattern we use to convert a stateful function into a stateless one. So basically we had state, which was just number n. In the case of a simple counter, we have this stateful method. So especially like in particular, we had this method called count. We are passing some arguments in general case, and we get back the output. Now we converted this, and instead of saving the state inside of the class, we're passing the state inside here as an input, and we return back the tuple, so the output and the state. And this pattern can be applied to any stateful class to get a stateless one, and that's cool. Okay, that was step one towards building fully fledged neural networks. Now, the second step is we still need to find a way how to deal with gradients. And you may wonder why we have to learn anything new to deal with gradients. Well, we already know about the grad function. Well, the thing is, with our current knowledge, we would go something like this. So imagine we have some loss function, f, and we have the parameters of our neural network, so x, y, z, and w. So we basically only have 4 parameters for now. And we do something like x squared plus y squared plus z squared, blah, blah, blah. So basically we get, this is L2. You can treat this as L2 loss. So minimizing this loss would cause the weights to go get closer to 0. And now the problem here is if we had something like GPT-3 model, which has 175 billion parameters, and some newer language models are even bigger, basically you'd have to write 175 billion terms here, minus 4 that we already have here. And that sucks, right? So the problem does not stop there. Basically, if we now try to find the gradients because we want to do an update of our neural network parameters, we'd have to get df dx, so we have to find derivatives with respect to every single one of those arguments. And grad, as you recall, usually by default returns the a derivative with respect to only the first argument. So that will be df dx. So we have to explicitly pass this list of integers, and in the case of 175 billion, would have quite a lot of these, right? So this will not scale. And yeah, let me just run this. This is going to work as expected, but as I said, it's bothersome and it does not scale. So we had 2's because if we take argument df dx, it's going to be 2x, 2y, 2z in the case of df dz, etc. So basically, because we input all ones as the input, we get 2's for every single gradient. So that makes sense. Now, again, the problem does not stop here. If we want to do an update, we'd have to have 175 billion lines doing these types of SGD updates. So basically learning rate, gradients, and we update our weights here. So there is obviously a better way. This is just the motivation for why we need the following solution. And the solution is called PyTree. So in general, we are used to wrapping our model parameters in some more complex data structures, dictionaries, or whatever. And PyTree is the JAX solution to how to basically find gradients of arbitrarily nested data structures. And let's see a simple example here. So this is just a contrived example, obviously. You can treat it as some type of a model parameters, very esoteric, but yes, nonetheless. Just stick with me here. We're going to first learn what PyTree is, and then we're going to see a real example. We're going to train a multi-layer perceptron really soon. Let's see how PyTree is defined in the official docs. So if I open up the docs here, if I go to tutorial JAX 101 and find the working with PyTrees here, okay, we have the definition here. So a PyTree is a container of leaf elements and or more PyTrees. So it has this recursive definition. Containers include lists, tuples, and dictionaries. So let's see how that maps to our example here. So basically we have a container here. So this whole thing is a PyTree. but this PyTree contains another PyTree here. And finally, this PyTree has a leaf 1 and a leaf a string, this character A. And finally, this object is also considered a leaf. The second, this is also a PyTree, this whole tuple here, and tuple, I guess. This is the leaf, 1 will be a leaf, whereas this thing here will again be a PyTree, and 2 will be a leaf, and 3 will be a leaf. There is a handy way to analyze this, and it's called this, from JAX, just import this tree leaves function. We're going to iterate through these PyTrees, and we're going to get the leaves, and we're going to finally print them in a nice format here. So let's see what the results here are. Basically, this first PyTree has 3 leaves, as we can see here. So 1 character A and a simple empty object. Let me see what else is interesting. So as I said, this is 1, 2, 3. All of those will be leaves. In the case of a dictionary, keys are not considered leaves. Keys are just like metadata of the PyTree node. So we're just going to have 1, 2, 3, 4, and 5 as leaves, as you can see here. And interesting to notice here is finally this array is going to be considered a single leaf. So we won't have 1, 2, 3 as separate leaves. This whole thing will be treated as a leaf. So that's something to keep in mind. Okay, so how do we manipulate these trees? There's a couple of neat and handy functions. So again, we have an example here of a simple PyTree. And what we do is we call this tree map function, and we just pass in the PyTree, and we define a function that is going to manipulate and work on top of these. It's going to process the leaves of the PyTree. And basically, what we expect is that every leaf will be multiplied by 2 in the case of this simple lambda function. So let's run this, and as expected, we get everything is multiplied by 2. So that was in the case of these single argument functions. In the case when you have multiple, like when your function has multiple arguments, I'm just gonna create a copy here, so a reference basically, and I'm gonna do simple addition, and this time we're gonna call tree multimap. So we have 2 PyTrees as input. We manipulate them using tree multimap, and as the output we get the PyTree again. So if I run this, we would expect same results, and yep, we have the same results here because yeah, just adding 2 same structures is the same as doing multiply by 2, right? Okay, so finally, worth noticing here is that the structures have to be the same. So here the condition was trivially, I guess, true because I just made this a reference. But in the case when you have 2 separate like data structures, you want to make sure they have the same structure, because if I artificially here introduce a change, so I just do a deep copy of the original object and I just append this list that contains number 23. And if we try to run this, we can see that list arity mismatch is reported as an error. So yeah, keep that in mind. And that was the last missing piece before we can train like a multi-layer perceptron. Hopefully you already know what MLP is. If you don't, let me just quickly show you some diagrams. And whoops, okay, we are in a really bad part of the internet right now. Let me go to images here. If this thing will load. My internet is really slow today. Okay, so I'm gonna just type in neural network here, and hopefully everything will work correctly. And here we are. Here is a simple MLP. Basically, you have your input data coming in from the left. You're processing the inputs using these neurons. These are called hidden layers. This is the output layer, and out comes 2 results. So this thing may be like a binary classifier, like a hot dog or not hot dog. I don't know. In any case, that's MLP, at least on a high level. And now, okay, we're ready to start training a toy multi-layer perceptron model. So we know how to handle state. We know how to handle parameters, i.e. to find gradients of our parameters, which may be stored in certain types of nested data structures. So that's everything we need to train our first model in JAX, I guess. So let's start here. We have this init MLP parameters function. What it's going to do is return a PyTree object. And here you can see we specify the type, basically the configuration of our MLP. So it's gonna have 3 layers. So the first one will map input that's a scalar into 128 dimensional vector. Then we're gonna have a mapping from 128 to 128, and finally we're gonna have a mapping from 128 to output scalar again. So that's 3-layer deep MLP. So this function here just takes that list as an input. As you can see here, using this smart indexing, we can just fetch tuples such as this. So we first have the tuple 128, and we're going to use that to form weights and biases of our like a linear layer, and we're going to wrap it up into a dictionary and just append to this list. So this is going to be a list of dictionaries which contain two keys, weights and biases, which then contain like a randomly initialized matrices, and you don't have to worry about this. This is just a specific type, I think k-mean or something, initialization. Doesn't matter. And thing to notice, we're using NumPy random here instead of using JAX PRNG. Doesn't matter for this simple example, but just keep that in mind. Anyways, so we get back the PyTree, and because we have a PyTree, we can nicely use the tree map to print certain like information about the PyTree. And we can see we've done everything correctly. We have biases and weights. Everything is of correct shape. In general, this is a good practice to have to analyze the shapes of your data and model parameters and whatnot throughout the whole pipeline, basically. Okay, let's continue here. We're gonna have some update function here in order to train it. This is the main part, and I'm just going to, before we even start digging into the training code, I'm just gonna comment on the training code. I'm just gonna comment on this forward because we haven't defined it yet. And I'm just going to show you the input data. So this is what we're trying to learn to regress. So the MLP will have as an input a simple scalar, and we're trying to regress the corresponding y, which is simply x squared in this example here. So now let's see how this thing works. So let me uncomment this. Basically, we'll have a couple of epochs, so 5,000 epochs in this example. We're going to call the update function, and you see the pattern again. We are passing in the state, which is the model parameters in this case, and we return back the parameters again, and we just iterate that, and that's it. That's going to update the parameters, and finally we can regress using the forward method. Let me show how those are defined. So update basically takes as an input parameters x and y, so that's the input and output data. We calculate the gradients of the loss function with respect to basically this input data and the current model. Just stick with me. I'm going to analyze this in a bit more detail in a couple minutes. For now, let's just see what the loss function is. So it's a simple mean squared error loss. Basically, we do here prediction. We find an error term that's basically predicted y minus the ground truth y. We square it to get basically positive values, error terms, and then we do the mean across all of the data points, and that's your MSE loss. Forward is fairly simple. You have this is basically your MLP feed forward pass. So remember, params is a PyTree. When we iterate layer, is just a dictionary that contains weights and biases. So we take out the weights, we do dot product with the input data, and we just add the biases here and then apply the activation function value in this particular case. So there is a dichotomy we made here between hidden layers and the output layer. The reason is the last layer will not apply an activation function. We're just gonna return back the raw results. That's the reason for this dichotomy. I guess we can rewrite this a bit nicer, but yeah, it works. Okay, that out of the way, let's now focus on this part. We do the grad of our loss function, and as you can recall, basically it's gonna do a derivative with respect to the first parameter. And since our first parameter is params, and which is a PyTree, we'll basically get as the output the same structure as params, but instead of values instead of the weights, we'll have derivatives of those weights with respect to the loss function. So that's the magic behind grad. Basically, all of these built-in functions, transform functions such as grad, know how to handle PyTrees, and this is finally a concise way to solve this problem of figuring out the gradients. Now that we have gradients, we can use our loved tree multimap function, and we just pass in parameters and gradients. We have this, so on every single leaf of these PyTrees, we're going to apply the following rule, and that's from the weight, just subtract the learning rate times the gradient, which is simple stochastic gradient descent update rule, and that's it. As the result, again, tree multimap, as you recall, it returns back the PyTree like structure again, which means we have the updated weights getting back as the output of update, and we can see that here. So params in, params come out as well here. Now let's try to run this, and then we're gonna play a bit with this code. So let me run this cell. Let's see what I ran this one. Yeah, I did. So let me run this one, and let's see what the results are. Okay, this is the output. We can see a pretty nice fit in this particular case. We can now play with this function. We can try and see some other polynomials, maybe x cubed. We can see it also manages to fit this curve as well. We can play and add some other types of polynomials, something like this. I just added plus x here, and it's still like you can see at the borders here, because we have less data points. The fit has bigger errors compared to where we have a dense sampling, which is expected, I guess, right? Finally, let's try one more interesting example. That's sinus xs. Let's see what we get here. Whoops, we're gonna use numpy sine here. So this should work now. And you can see the fit is way worse here. We can obviously improve that by increasing the capacity of the model or increasing the number of epochs. But yeah, let's try some other frequency like 3x, and yeah, we have a much better fit here. In any case, you get the point. We trained our first neural network in JAX, and it seems to be working. So let me return back the original statement here. So that's a simple like a polynomial. And now let's analyze a couple of things here. So first, let's see the structure of grads. I'm gonna reduce this to 1, just a single epoch. I'm gonna comment out the JIT part, and I'm gonna print grads here. Okay, so I'm gonna just print the gradients here, so that we are confident that we get the same structure as params. So I'm gonna run this cell. I'm gonna run this again. I guess the output is going to be a bit unwieldy. Okay, let me see what we got here. Bunch of numbers, but you can basically see that we have a list of dictionaries where the keys are biases and weights. And basically, these numbers are derivatives and not the parameter values. That's the important part. So that's this part. Let me just uncomment this, return back the JIT. And I mean, that's pretty much it. That's everything that goes into training an MLP. As a quick mention here, you can notice that I called JIT on top of this high-level update function, because it gives the XLA compiler much more freedom to optimize various functionalities inside of this update function. You can obviously play and toggle off and on the JIT wrapper here and see how faster it is to train it with JIT compared to without JIT, I guess. Yeah. Okay, let's continue here. This was an example of a simple neural network, but if we wanted to create our own neural network library, we'd need to create layers such as NN linear, that's just PyTorch syntax, or conv layers, etc. And in order to get those to work, we have to create our custom PyTrees. And let's see why that is. So first, imagine this main container object here is just a simple NN linear layer. So let's imagine that's a linear layer, and now imagine we have a list of 2 linear layers here. So I just created an example PyTree here, and now let's fetch the leaves and see what we get as the output. And we would expect, I guess, like 8 leaves here, right? But the thing is, it's going to return only 2 leaves. So we have here that this whole PyTree only contains 2 leaves, and those are this main container objects. That's obviously going to be undesirable, because tree map and those other functions, they go through the leaves and they do certain updates. And if we had a linear layer like this, we wouldn't be able to do gradient, like stochastic gradient descent update on top of these structures. So we have to find a way around this. For example, if we were to run this simple manipulation, so just x plus 1, we'd expect to just increment these numerical values, but this is not going to work. And I guess it makes sense, because if you know how tree map works, it's going to iterate over the leaves, and the leaves are my container objects, and we're trying to add 1 to a my container, which doesn't make any sense. So let's run this. and we can see that we got this error. We're trying to unsupported operand blah blah plus for my container and integer. So that makes sense, right? So what's the solution to this? It's simple. You just have to define two functions. One is flatten, one is unflatten, and then you have to register a PyTree node. So we register the my container with these two associated functions, flatten and unflatten. So what flatten does, basically you just take the ABC, so those were the values we had here, right? We'll just wrap that information into an iterable here, and we are not going to want to have a name as the content. We want to have it as a metadata, and that's why we include it in this auxiliary data structure, and we just return this tuple like content and auxiliary data. Finally, the unflatten just receives those same inputs in reverse order though, because of, I think, some legacy problems they had. And you basically just construct the my container and you return it back. That's it. So after I run this, now the my container class should work as expected. So if we were to run the tree leaves function again, let's run it, and we have the leaves 1, 2, 3, 4, 5, 6 as expected. Now this thing will work. So if we were to add +1, we'll just get, I guess, 2, 3, 4 should be the output here, and yes, that is the case. Basically, tree leaves, i.e. the tree map, iterated over the leaves, which are just the numerical values here, these ones, and it just added +1, returned a PyTree again, and we just print the leaves here. That's it. There's one more gotcha I wanna tell you about, and that's that we can oftentimes mistake nodes for leaves. And when I say that, here's what I mean. So let's create a 0 PyTree. So basically we just have two nodes here, two leaves that contain zeros with these shapes. And let's try to create the same type of PyTree that will have ones instead of zeros. So what we do here is we create this intermediate PyTree. We're going to iterate through the zeros tree, through all of the leaves. We're gonna take the shape, and that's gonna be our new PyTree. And then we can iterate through the shapes and apply the ones function using tree map to get like the tree of ones. And let's see whether this works or not. So if I print it like this, here's what we get. We get correctly 2, 3, so we have 2 rows here and 3 columns, everything is fine. We have 3 rows here and 4 columns, so everything is fine here. It seems that we have a correct result here as well. So we have 2, 3 shape and we have 3, 4. So that's the intermediate array. So this shapes tree here. And finally, we have some weird result here. So what happened? So the thing that happened is, if you can recall, basically this here, this whole thing is a PyTree, but this tuple is a PyTree as well. It's not a leaf. That means that leaf is 2 and 3 and 3 and 4, which means we're going to apply ones on top of all of these leaves, and that's why we get 2 ones here, and then 3 ones here, and then 3 ones here, and 4 ones here. So a simple workaround here is to create, so we want to make sure that this is a leaf and not a PyTree. We can just basically wrap this x.shape with JMP array, and this should now work. Let me see. And yep, it works. So basically the reason is this is now a leaf, 2, 3 are a leaf, and we pass that to ones, and that's why we get correct results here. Awesome. Now we can design custom neural network layers, and we can train end-to-end our neural networks. Now, what if we want to train really big neural networks? Well, in that case, we have to parallelize our computation, and that's where this next section comes into play. So I'm going to introduce this pmap transform function, and as we'll soon see, it's very similar to vmap. But before I start showing you how to use pmap, we have to do a couple of things. So the first thing is to set up, we have to use TPUs here for this section. So I'm going to set up hardware accelerator to a TPU. I'm going to click save, and hopefully after clicking reconnect, it's going to allocate a couple of TPUs for me. Awesome, this worked. So now I just have to rerun the import statements because interrupting the runtime erases all of the whole state of the collab. So we have to rerun this cell, and then let's go back. I can open it up like this. Just jump to Parallelism in JAX in the table of contents, and we are here. Okay, so we're first going to just call this setup function, and that's gonna set up TPUs in the background, and hopefully we'll get 8 cores at disposal. Okay, running this cell may take a while, but finally we got 8 cores here, as you can see. So 0 through 7. Now I'm gonna use this convolve function as a running example, and we'll be parallelizing this particular piece of computation across multiple cores. Although we'll later see training a neural network, actually a simple ML model across parallel cores. So let's start with convolve. So I'm gonna define a simple signal here. So we have a signal X and we have a kernel W. And the convolve function works as expected. Basically, we are sliding W across X. We are doing dot products, and we are storing the computations in this list. And then we're just converting the list into like a JAX array. That's it. Just a simple 1D convolution. So if we run here, let's see the results. And we get correct results. So basically, imagine, let me print X and let me print W as well here, so that may make a bit more sense. So what we do is in the first basically computation, we'll have 2 times 0, that's 0, 1 times 3, that's 3, and 2 times 4, that's 8. 8 plus 3 is 11, and that's why we get 11 as the first output. That's all nice and clear. So now let's do the same thing, but this time let's parallelize the computation. So first, this is just going to grab the number of devices on disposal. We'll have 8 cores, and then we're just gonna create a batch to simulate heavy load, so some like bigger computation compared to just having a single signal X and kernel W. So let's run this, and basically we get we have 8 devices, and that's why we end up having a batch of 8 times 5, where 5 is basically the signal length, and we're just replicating. So here we have unique data for all of these 8 elements in the batch. On the other hand, we're just duplicating the kernels. We're not creating novel kernels for each of the examples. Okay, that's it. Let's now first parallelize the computation across the memory of the host device. That means we'll be using a single core, but VMAP is gonna parallelize the computation in the background across I guess even multiple threads. I'm not sure how it's exactly implemented. Basically, we wrap the convolve function into VMAP. By default, it's gonna assume that the in-axis argument is set to 0, 0. So this is the equivalent to explicitly writing in-x is equal to this tuple of 0, 0. And after we run this, we'll get the result. And as you can see, this part is the same as the example above. And then we have increasing numbers because the signal X is being... let me print X here. Let me just print this batch. You can see we are going from 0 through 39, and that's why you can see increasing numbers here as well. The cool thing about PMAP now is that we just need to swap VMAP for PMAP, nothing else changes, and all of a sudden we're sharding our batch of data, so the signal X across multiple cores, and we're running the computation in parallel independently on each one of these cores. So let me run this, and we get the same results as you can see here above for VMAP. There is one difference you can notice here. So this thing is called device array, whereas here we have sharded device array. So this sharded alludes to the fact that the actual data and computation is distributed across multiple cores. So that's super cool. So syntax, same as VMAP, and that's nice and sweet. Let's continue. And I wanna stress that all of this happens literally independently. So basically, we have 8 signals. So recall that X was 8 times 5. What will happen is that array of 5 elements is gonna be on each of the cores alongside the kernels. So we basically have a single computation. So we have a single kernel and a single example on each of the cores, and we are doing computations without communicating between the cores. So that's super nice if the nature of our computation is such that we do not need a communication between the cores. And here I'm just illustrating that we can do one pass of this computation. So we do a convolution 1 times, and then we use the outputs as the kernels, as the new kernels, and we again convolve them with the original signal x. And basically the thing is, during both of these two calls, we did not have a single communication between the cores themselves. So let me run this, and we get some even bigger numbers, and that's not that important anymore. Finally, just notice that instead of like replicating W's, which is kind of wasteful, right? We can just use the in-axis argument here, and as you recall, like VMAP uses the same syntax. Basically, in-axis tells PMAP that the first argument, so that means W, basically should be broadcasted because we set none here. And here it means like 0 just means that the zeroth dimension of XS is corresponds to the batch dimension. So this way, the PMAP will in the background replicate W and do the job for us. So that's way better. And let's run this, and we should see the same results as before. So 11, 20, 29, 326. That was the same number as here and elsewhere. So that's the same output again. Okay, so again, this is super nice if your computation is such that you do not need communication between the cores. This is usually not the case, and an example we'll soon see is the one of training a ML model in a distributed fashion, whereas we take our batch of data and we basically split the batch of data into mini batches. We send each mini batch to each core, and then we do computations there. We calculate the gradients, and then we communicate between the cores in order to do a mean of the gradients to update our ML model. We're gonna see that example in a second, but just be aware that certain computations do require communication, certain do not, and JAX got us covered for both of those use cases. So now let's see a simple example, like just a modification on the above function that we had. So this is going to be normalized convolution, and the only difference is that we'll have a communication between cores. So let's see how this works. This part of the function remains totally the same as before. So we have output here. We are doing like sliding across the signal, and we accumulate the results into output. Now the only difference is that we are calling this, so remember we're calling this JAX Lex psum function, and just recall that Lex is this middle layer API of JAX. So what we're doing here is we're going to, along the batch dimension, we're going to sum up all of the outputs, and we're going to divide output on this particular core with the sum of outputs across all of the cores, and that's going to normalize our output. So a thing to notice is this axis name. It can be a bit confusing. So what you do is you again wrap your function of interest into PMAP. You specify in-axis, which means, hey, I want to broadcast W. I want to use the 0th dimension of XS as the batch dimension, and we just give the name to those mapped axes by putting an arbitrary name here. So this can be whatever. Like, we just need to have a consistency between whatever we use here, we have to use here inside of the definition as well. So I chose batch dimension because it's I guess indicative of the thing we're doing, right? Let's first run this, and then we can analyze it additionally. The first thing you can notice is that this output is the same as VMAP. So I just did that for you to understand that VMAP and PMAP are conceptually very similar. The only difference is that PMAP is actually using physical cores, whereas VMAP is doing the same thing just on the single device. So let me just comment out VMAP so that we can have a bit less output in the console here. So basically, what the normalization has done, it's that all of these columns are now normalized, meaning if we sum them up, if we take a single column like this one, and so this one, like this element and this element and this element, and we sum them up, we're gonna get 1. So that's what I've done here. I took the result, I took all of the rows and 0th column, and we can see here that the result sums up to 1. If I put 1 here, we're gonna get the same result, so it's again 1, and if I put 2 here, we're going to get 1 as the output, and that's it. That's what this computation did. Let me try and see whether we can print the output here. I'm not sure whether this is going to work. Let me just try and do this. Nope, it's gonna trace it because PMAP, that's an additional thing to keep in mind. PMAP is automatically calling JIT in the background, so yeah. To make this a bit more clear, I'm going to take the last example that didn't have any communication. So let me take something like this. I'm just gonna copy paste it here. So we're just gonna copy paste that thing here. Okay, now we have a result here that is not, I'm gonna print it here. So pmap result, and this result is, there is no normalization here. So let me just print it out here. So here are the results. So what we have done is this psum, basically alongside batch dimension, which is this dimension here, so the vertical dimension, is going to sum up all of these values and use them to divide the current output. So for each core, for example, for core 0, this will be the output, and we're going to divide this array here with the sum across this dimension of the vertical dimension. So let me just kind of show you that that is the case. So if I was to take the element number, like this element here, 11, so that's going to be temp element, something like this, I don't know, pmap result. Basically I'm going to take 0th, so that's this first row. I'm going to take the 0th element, so that's 11. Let me confirm that's the case. So I'm going to print it, and then I'm going to create a temporary sum here. So basically just a simple sum of pmap result across the vertical dimension, so that's the batch dimension, 0th column, and I'm going to print the sum as well, and then I'm going to just do division. So I'm going to print temp element divide by temp sum, and we should get the same result as here, so 0.0081 whatever. Okay, so in order to make this a bit less crowded, let me see whether I can do something now. Let me just run this. This should work as expected now. So I took 11, I created a sum here, and after dividing you can see we got the same result. So hopefully this now is perfectly clear what happened, and the whole magic was because of this middle level API's psum function and just giving a name to these mapped axes here. Let's continue. Let me just erase this output. Okay, now before we get to the final training pipeline, there's a couple more functions you should be familiar with, and then you can train whatever in pure JAX, pretty much whatever ML model you wish to train. The first function is this value and grad function, and it's going to return the value of the loss as well as the gradients of the function of interest. So I have a simple loss function here. It's basically just we just create these error terms, we square them, and we sum them up. We have a simple input here, so that's, let me just print it here. So basically it's going to be 0 through 3, and finally the value will hopefully return the loss value as well as the gradients. It's fairly trivial to show that the numbers make sense. Let me just print y here as well. So it's going to be the same as x, just plus 0.1. So basically the value of the loss does make sense because we basically subtract, the difference will be 0.1 for each element here. Then we square it, which is going to give us 0.01, and we have 4 times that because we have a sum, so that's why we have 0.04 here. Same goes for gradients. All of the gradients are minus 0.2 because the derivative with respect to x will be 2 times x minus y. The difference is 0.1. I mean the minus 0.1 times 2. That's why we get these numbers here. So, and in any case, if you want to log both the value of loss and you want to get your gradients, you have this efficient way to do that is to just call this inbuilt function called value and grad. The second function you should be familiar with is, not the function actually, just the functionality, is if you want to return sometimes from your loss function, you want to return not just the loss itself, but maybe also some intermediate values, like maybe you want to return these raw error terms. You can just, instead of doing this, so if I were to call gradient function on this loss function here that has 2 outputs, which means a vector output, we're going to get an error here because gradient only works on scalar output functions. So you can see here gradient only defined for scalar output functions. So there is this neat has auxiliary like flag. If we set it to true and we run this, it's going to return the gradient as well as the it's just going to pass this intermediate value as the output directly without doing any type of manipulation on top of it. Awesome. We are now ready to train a machine learning model completely in parallel. Okay, let me see how I can go about explaining this part, because there is a lot of functionality here, but I think it's going to be digestible. Let me first start by analyzing our data. So we have a simple model, the ground truth model is this one, basically a single input linear function here. With some addition of noise. It's a we'll have some noisy observations here. So the true number, the true value of W, so the coefficient that goes with X, and of this bias term are 2 and -1. We generate the domain of our data, basically just sampling from the normal distribution. We generate 128 elements. We generate some noise, again, sampling from the normal distribution, and finally we generate our noisy observations by applying the above function here. So XS times the true value of the weight parameter plus the true value of the bias parameter plus the noise, and let me visualize that for you so that we understand what we're trying to regress. So we're going to try to fit a line to this data, and we're going to do that the following way. So first, we'll need to initialize our model. So let's jump to the init model function here. It's going to initially create a random value for the weight and for the bias. So this is our approximation of the true weight and the true bias values. Initially, the best we can do is just to create a random value and return them packed into this params class, which just inherits from this name tuple. So it has weight key and bias key, and the values are JAX arrays. As you can see here, I'm using JAX's built-in PRNG functionality. So I'm using the random number generator. I'm splitting the keys into weight and bias, and I'm consuming those here to generate two random numbers. So that's what this init model function does. Once we have that, I'm going to fetch the number of devices. That's going to be 8. If you recall from the previous exercises, we had 8 cores. And we're going to replicate the parameters because we want to shard we want to replicate this particular model across all of the cores and do the computation in parallel. Since params, so the thing we just got from our init model function is a PyTree, we can iterate over the leaves, so over the weight and over the bias, and we can just multiply them by 8, which is going to replicate the values. So we'll have, I'll just gonna print it here so you're gonna see it in a second. Next thing we're gonna do is just reshape the data for the pmap function, because we're gonna trade this in parallel again. So we have the XS and YS, so that's the data we just saw here, and we're gonna basically just reshape them so that the leading dimension has the number 8. So let me run this and see what we have. So okay, I forgot to run this cell. I'm gonna run this cell, and then I'm gonna rerun this cell again. And let's see what we got here. So you can see a couple of things here. First thing, weight and bias have the same number replicated 8 times as expected. And finally, the data is now reshaped into this 8 times 16 times 1 shape, which is suitable for pmap. The basic training pipeline will look very similar to the MLP we trained like 20 minutes ago. Basically, we're gonna have a number of epochs. We're gonna iterate for a certain number of epochs. We're gonna have an update function, and again, the familiar pattern. We pass in the replicator parameters, we pass in the data, and we get back the parameters, updated ones, as well as the loss value. After that, I'm gonna just log some values here, and we're gonna see that in a second. And finally, we're gonna take our final replicated parameters, and we're just gonna fetch parameters from a single core, because we'll basically have 8 duplicates across the cores. So we just need to extract a single one, and we get parameters here. So tree map will create a PyTree object, and then device_cat just takes the data from the TPU and downloads it to the host memory. That's it. Now that's the high-level picture of what is gonna happen here. Now let me start digesting these couple of functions here. So what we need to understand is that the model is very simple. We just have weight times XS plus the bias, because that corresponds perfectly, because we know what generated our data, so we can create the same model here. Usually that's not the case. You usually don't know how your model structure looks like. That's why you have a huge like a neural network, and you let the data morph the structure of that neural network. Loss function is very simple. we just basically do mean square error again. So predictions, we subtract the ground truth, etc. The update function is by far the hardest to understand, so we're going to focus a lot on this function. So let's see what update function does. So we get our parameters, so that's the current version of the parameters. We get the data, and what we do is first we decorate the update with this pmap, and we name the mapped axis to batch. So this is just a convenient way to if we do it like this, then we don't have to wrap it inside of the pmap here. So let me show you. So here, as you can see, we don't have pmap explicitly here. We just decorated update directly with pmap, and that's why we can avoid putting pmap here. So what will happen is that each TPU core is going to get a portion of the parameters. So because those are replicated, we're just going to have the same parameters spread out across every single core. We're going to get a single mini batch out of the whole batch of data on each of the cores, and then we're gonna pass those into the loss function and find the value and so the value of the loss as well as the gradients of the loss function. So that means because again grad does the derivative with respect to the first parameter, which means we're gonna have derivatives with respect to W, the weight, and the bias. Next thing we're going to do is we are going to combine the gradients across all of the TPU cores, and this is arguably one of the most important operation in this whole training pipeline. Basically, you take the gradients which are now different across each of the cores, and they're different because each core got a different portion of the data set. Whoops, I'm not a robot, I assure you. So basically, you're gonna do a mean averaging across all of the gradients, and finally, each single core will have the same gradients because we do this p-mean operation. As a consequence, because we also have the same parameters, that means that each core will have the parameters in sync. So all of the parameters are initially the same, the gradients are the same, which means that the updated parameters across each of the cores are also the same. So that's cool. We did the same thing for loss. We just averaged the loss across the 8 cores, and finally we apply the stochastic gradient descent update rule. Again, we have PyTree here. We just do the usual from the current value of the parameter, we subtract the learning rate times the gradient, and that's how we get our new parameters. Finally, we're going to return those parameters as well as the loss value, and that's it. I made a short note here which may be important if you want to train with some more complex optimizers and not just with SGD. So if we had an optimizer, this is how the pattern would look like. We pass in the grads, and we pass in the optimizer state, and the optimizer, because of, remember our pattern, is going to return the new optimizer state and the new basically updated version of gradients. And then we could just apply the updates instead of grads here, and that's it. So it's very simple, just another additional line following this stateless pattern that we saw in the beginning of this video. Nice. Let me now go and run the training. So this is our training. Let me run it and let's see what we get. Okay, it's working. We're printing some values. We're going to debug and analyze what's going on in the console here. But before that, let's just plot the results. Okay, so let me run this. And we see that we have a line that's fit to this particular data set we artificially built. Now let's analyze the output in the console. What happened here? First thing I want you to notice here is that replicated parameters, because as I said, those are going to stay on the cores, they should be sharded device type. So let's see whether that's the case. So we can see here after printing after the 0th epoch, we're gonna have, this is a class of blah 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 sharded device array, which means that indeed our replicated parameters are on the cores themselves. Loss is as well a sharded device array, but the data is, as you can see here, I'm just printing the type of the data. We can see it's a NumPy array, which means it's locally stored on the CPU, because we do not want to keep the data on the core. That wouldn't make any sense, especially for bigger data sets. Finally, what I'm printing here is the loss shape. You can see it's a 8-dimensional vector because, again, it's sharded across different cores. And we can see that the loss goes down as we are advancing here. It gets into saturation after already a couple hundred steps here, but yeah. And that's pretty much it. We trained our first machine learning model in parallel on 8 TPU cores, and as you saw, it was very simple to do that. Now you're almost ready to be able to train whatever type of machine learning model. There's a couple more questions you have to get an answer to. So how would you go about doing transfer learning in JAX? Relatedly, how do we freeze certain layers and fine-tune other layers? So we need to figure out how to do that, how to do stop gradients. And finally, how do we get per sample gradients instead of the usual per batch gradients? I'm going to tell you all about that in this last section of this tutorial. In order to demonstrate how stop gradients work in JAX, I'm going to use a couple of examples. So first things first, JAX uses this JAX Lex stop gradient primitive for this purpose, for stopping gradients. Let me quickly go through this TD0 update rule here. If you're not familiar with RL, this may be super confusing, but you do not need to know what this is. You just need to know some of the details, which I'm going to explain to you right now. So the whole point is we are trying to learn certain value functions. So that value function in our example is going to be a simple linear value function. So it's parameterized by theta. And we are basically doing dot product with the state vector in order to get the value function. So in order to find the gradients of theta, we have to do this expression. So basically we have a reward here at the present timestamp plus the value at this at the current state minus the value at the previous state, and we multiply that by the gradient of the value function in the previous state. So that's a mouthful. The whole point is the update is not a gradient of any loss function. However, if we reformulate this above expression into this thing, and if we have a way to stop the gradients of this target here, of this value at the present state, we'll be able, by doing a gradient of this pseudo loss function, to get exactly this expression. Again, as you can see here, if we ignore the dependency of the target on the parameter theta of our value function, we're going to get exactly this. So let's see why that is. If we do a gradient with respect to theta, 2 goes in front here. We'll have this whole expression, and then if we do a derivative with respect to theta, and this does not depend on theta, that means we're just going to end up with the derivative of this previous value function at the previous state. So that's exactly this expression here. So just some basic rules of differentiation at hand, that's all. So let's finally see how we can implement that. We have the value function, as I already explained, simple dot product. We have some initial values for the theta. We have some state. So this tm1 just means timestamp minus 1, i.e. the previous timestamp. We have the reward. We have the current state here. And finally, we have the TD loss. We calculate the value function at the previous state. We calculate the target, and this is the whole point here. We just apply the stop gradient to target, and this is going to be our loss. And now when we do a gradient of that loss with respect to theta, because theta is the first argument here, and remember again, gradient by default will do a derivative with respect to the first parameter, we get the correct value of delta theta here, i.e. the gradients of our model. I'm going to run this, although the number will not mean a lot, and I don't think it's that important to go and analyze this further. You get the point here. The second example is this straight through estimator, and I've seen this thing used for example, in the VQ VAE paper, and I also covered that paper in one of my previous videos. You can check it out. I've basically pasted the link here. But the whole point is, if you have a certain non-differentiable function in the middle of your neural network, for example, this is a simple non-differentiable function. You take the x, which is a float, and if you apply a rounding, that's simply not differentiable. So now we can reformulate this non-differentiable function into this straight through f. So basically, what we have done here is, if you take a look at this, so x plus f of x minus x, basically that means in the forward pass we're going to have f of x, which means these two are equivalent in the forward pass. On the other hand, if we do a derivative, if we find a gradient of this function and the gradient of this function, they are going to be different. So I just took some simple example here. So x is 5.6, just an arbitrary number. We're going to print the value in the forward pass. So we're going to see that those are going to be the same. So 6 and 6, because when we round 5.6, we get 6. So that's clear. Whereas because this f is non-differentiable, if we try to do a gradient at this point x or whatever x is, we get 0 all the time. On the other hand, this straight through gradient is going to give us 1 all the time. You can see why that is, because we have a stop gradient here. So a derivative of this thing with respect to x is just gonna be 1, because yeah, I mean, if a function is equal to x, then basically a gradient is 1. So why may this be useful? If you have a automatic differentiation in the reverse mode, you're basically, if you have 1 here, if a certain part of your whole function has a gradient 1, by multiplying the gradients that came from the deeper levels by 1, you're just going to pass them through. That's why it's called straight through. You're just gonna copy them to the second part of the network or whatever ML model you're using, and that's why this thing is kind of cool. But the whole point is, again, just be aware that we are using this stop gradient to achieve this functionality. Let's see a couple more advanced things. So calculating per sample gradients, and let me just read this through. So in many frameworks, PyTorch, TensorFlow, Theano, it is often not trivial to compute per example gradients because the library directly accumulates the gradient over the batch. Naive workarounds such as computing a separate loss per example and then aggregating the resulting gradients are typically very inefficient. So you can go around this problem by taking a single sample, so for example maybe a single image, passing it through, calculating the gradients for that single image, and then doing that for the whole batch in a kind of a for loop, and then aggregate the results, aggregate those gradients. But that's super expensive, as you can imagine. JAX basically has direct support for this type of a thing, and it's very efficient. So if we create a contrived example here by just stacking the state in the t-1 like timestamp, and we batch the rewards, we batch the current state, basically using VMAP is going to allow us to get these per sample gradients. Because remember, TD loss used to have, so it does not accept a batch of data. It accepts a single example, so a single state, a single reward, and a single state here. And we have arguments theta here. So if we map it, if we wrap it inside of a VMAP, using in-axis none, which means theta, so the arguments of our value, so the parameters of our value function are going to be broadcasted, and then we say 0, 0, 0, which means the first 0th dimension of these batches here is the batch dimension. If we do that, we're going to trivially get the gradients for every single example, and they are the same because we batch the same states here, so that's kind of trivial. Wrapping up this tutorial, which is already quite lengthy, in a summary, JAX like auto differentiation engine is super powerful. You can do various stuff. You can even define custom derivative rules if you have some numerical problems. That's now already super advanced. You can check out the docs here. I particularly linked this AutoDiff cookbook article, which you should read if you want to know all of the nitty-gritty details of the AutoDiff engine. I'm gonna end up by showing like a simple example of this MAML. So this is this model agnostic meta learning algorithm, and you can see it's fairly complicated. You can see the math here, and the whole point is this is how simply you can implement this MAML algorithm in JAX. It looks very much like mathematics, and that's why I think JAX is super powerful and useful for researchers. Not that beginner friendly, as I already mentioned in my previous video, but even for beginners, if you go across a couple of hurdles, I think it's gonna pay off. Let me briefly go over MAML. So the whole point here is, imagine you have a couple of tasks, and while training, you do not want to minimize the loss on any particular task. You want to minimize the loss, the potential losses on all of those tasks. For example, maybe going in this direction will minimize the loss for the task 1. Going in this one will minimize the loss for the task 2. And similarly, going in this one will minimize the loss for task 3. That would lead us to have either theta 1, that these thetas are going to minimize the loss on the task 1. Similarly, this theta here, theta 2, is going to minimize the loss on this task 2, and similarly for theta 3. But we actually move here, which is somewhere in between all of those thetas, and that's how MAML works. And now, briefly going over this meta loss function, we calculate the gradients here, and then we use the gradients to update, using SGD, we update the parameters here, and we pass that into the loss function. and then we take the gradients of that loss function. So it's kind of convoluted. I'm not gonna try, this is not a video about MAML, but I want you to just kind of appreciate how expressive JAX actually is. Having said that, hopefully you liked this video. If you did, share it out with your friends, consider subscribing to this channel, and also join the Discord community. That's where the party is. Until next time, bye bye.